Welcome to Microlecture 39. We're talking about the E2 mechanism in finer detail. Alright, so we have some considerations to think of when we're talking about E2 reactions. First of all, we want to write out the rate equation for the reaction like we did for our SN2. And we're going to consider a couple of different types of bases. And one of them is a bulky base that might yield actually the less stable, what you would consider to be the less stable alkene product. Okay, because bulky bases can only remove the most sterically accessible proton. And so that will result in a less stable carbon-carbon double bond. We'll see how that works. Other bases, they remove the proton that will result in the most stable alkene product. And lastly, a geometry consideration is very, very important here. E2 reactions must proceed through anti-geometry, all right? So that means there's a dihedral angle of 180 degrees between the beta proton and the leaving group, so like the halogen atom, for example. And so if we were looking at a Newman projection, then what we would see, if we were like looking down this bond, what we would see is that H and X would be anti to one another. And that geometry is absolutely required. So if it can't be achieved, sometimes on one side of the molecule, it can be achieved on the other side of the molecule and can lead again to the less stable carbon-carbon double bond, like the less substituted carbon-carbon double bond, or even stereochemical considerations. So sometimes Z forms instead of E just because of this geometry constraint. So the rate equation for an E2 reaction is the rate of the reaction equals rate constant K times the concentration of both the alkyl halide and the strong base being used. Okay, so again, bimolecular is the 2 in E2. That describes a reaction in which both of these species are important in the rate limiting step. And so if I were to map that out on an energy diagram curve, it would look a lot like an SN2 reaction, because we would have only one energy barrier to get up over, okay? We'd have only one activation energy. And so rather than being stepwise, we would call this a concerted reaction mechanism, where everything kind of all happens at once. Alright, so we're going to use the same compound to make the point about regioselectivity with bulky bases, and also the geometry constraint. So let's say that I'm doing this reaction with this alkyl halide, but I've got a bulky base. And the bulky base that's almost always used is tert butoxide. So this is a big, bulky tert butyl group here. So it cannot, sterically speaking, get into highly branched areas. And so if I go ahead and just label my, I'm going to label my beta protons. There's one there, and there's a couple there. Regioselectivity describes which proton are we going to react with this strong base. And it turns out that the more hindered region of the molecule, or more branched, is inaccessible to something so bulky as a tert butoxide. So it's going to come over here and steal a more accessible proton. and the electrons will kick in and we'll lose our leaving group. And so the product that we would expect to form here is this alkene, which is disubstituted, not the alkene that would be perhaps considered over here, which would be trisubstituted, if we had been able to react this proton here. Again, with the large amount of branching there on this tertiary carbon, it's just not possible for a bulky base kit to get in. And then the next thing to consider is a geometry constraint. And so we'll actually see now how the hydrogen atom that I chose up above was actually not the right one to choose. I would have chosen this one instead. When we're considering the anti-geometry that's required in an E2 reaction, what we want to do is label the beta protons and see what their relationship is to the leaving group. And so I'm going to label all of them. There's 3 of them. And I want the H and the iodine leaving group to be anti to one another. That means they have to be in a dash wedge relationship opposite each other. I can't have wedge wedge or dash dash. So for that reason, as it's drawn at the current moment, I would not be able to react the base with that proton, okay, because it's on the same side, not anti, to the iodine leaving group. But we can luckily take care of that in a non-cyclic system because we have rotation about carbon-carbon bonds. So let's think about rotating about this carbon-carbon bond until we get hydrogen pointed anti, which would be on a wedge relative to the iodine leaving group. And so you'll need to develop the skill of carbon-carbon bond rotation here. So my iodine is right there, and if I hold that part of the molecule steady and only rotate about this carbon-carbon bond, then I end up moving the ethyl group over onto that side, and then the hydrogen and methyl group end up over here, such that this is the hydrogen now, and this is a methyl group now. So now, through just an allowed carbon-carbon bond rotation, now I can actually proceed with the mechanism and take the base, abstract this proton right here, kick the electrons in, and lose iodine. And so let's think about the stereochemical consequences then of doing that. So the double bond forms here, and I have a CH3 group. Reminder to never draw a dash or a wedge on an sp2 hybridized carbon atom because it's flat. Okay, so no dash wedge. The issue here is that we've formed a Z alkene, which is less stable than E, and it forms as the major product because it's the only product that can form in this case, given the constraint that the geometry must be anti. All right, and if we were considering reacting on the other side of the molecule, well, this isn't a bulky base, and so it's an ordinary base, and so it's just going to abstract the proton that's going to yield the most substituted product. Okay, so this tri-substituted alkene will form and not the dye-substituted alkene on the other side of the molecule. All right, so do practice these. There's lots of drills available. Practice predicting the products and distinguishing between E2 reactions and SN2 reactions.